Hi everyone. So today we have Emma Phillips who will be speaking on Principle 2 group bundles.
So thank you, Sarah. Thanks for organizing this whole seminar. It's been one of the few perks of the pandemic is having these virtual seminars going. So I'm Emma. I'm a student at the University of New Hampshire, and I'm going to talk today about a project that I've been working on for the past 2 years as part of a kind of large collaboration with Dan Berwick-Evans, Emily Cliff, Laura Murray, and Apurva Nikade. So this came out of one of the AMS mathematics research communities, one from 2019. And if you ever have an opportunity to go to one of those, I highly recommend it. You get to go spend a week in a pretty area in Rhode Island and work really intensely on one research field. And even if you don't have background in it, there are mentors to kind of help you get into a project, which was absolutely the case for me with this project. So I'm going to give an overview of the big picture, which is going to have a lot of words that probably don't necessarily make a lot of sense to start, and then we'll try to talk about some of these in some detail. So we've been working with two groups, specifically ones that you can think about as a categorical extension of a finite group G, classified by a 3 cocycle alpha. And for a Riemann surface X of genus G greater than 0, we've shown that there's a forgetful functor from flat principal 2 group bundles to flat principal G bundles over X, where the fiber of this forgetful functor over one of these flat principal G bundles is the bicategory of trivializations of a specific 2-gerb depending on the bundle and alpha. We've also shown that this forgetful functor is actually what you can call a 2 fibration, which categorifies the free Quinn line bundle over flat G bundles. And then we've also shown that given particular restrictions on X, we can give complete invariance of these flat 2 group bundles. So today I'm gonna give some overviews of these things, but for most of the kind of detail work, we're gonna think about the case where X is an oriented 2 manifold. So basically you wanna keep in mind a torus as your example of X throughout, which simplifies things a lot and allows us to make some algebraic constructions. So I'm going to do an introduction to what 2 groups are with lots of examples. We'll talk about one notion of principal 2 groups, and then that special case when X is an oriented 2 manifold. And then we'll think about some other connections that we can use these principal 2 groups for. Okay, so a 2 group, or what's sometimes called a categorical group, if you're hanging out with algebraists and don't want to confuse them, is a monoidal groupoid where each object is weakly invertible. So when we talk about a monoidal groupoid, we mean a category that has a tensor or multiplication structure. When we say groupoid, we mean that all morphisms are isomorphisms. And when we say that each object is weakly invertible, we mean that for all X in our 2 group, there exists a Y in the 2 group such that X tensor Y is isomorphic to 1 and Y tensor X is also isomorphic to 1. And of course, when we have a monoidal category, we also have a sense of tensors on the morphisms, not just the objects. So we're going to primarily focus on 2 groups. We'll talk a little bit about smooth 2 groups as well. So 2 groups we're thinking of as this categorification of groups. And then when we think about smooth 2 groups, we're thinking about that as a categorification of lead groups. So we'll see that we can get from a 2 group to a smooth 2 group in the same way that we would kind of get from a group to a lead group. In other words, adding a topological structure to it. Okay, so the first easiest example of a two group is just starting with any group H. We can define a two group that has objects just H in H. Morphisms are only the identities. And then our multiplication structure is given by G tensor H is just equal to GH, the multiplication from G. So normally when we talk about a monoidal category, we need an associator as well. But in this case, our associator is just the identity since we only have the identity morphisms anyway. Okay, so this is a very, very simple two group, but it's one that we will come back to over and over again. And then our other like major, but still simple example is for abelian groups. So in the previous example, everything interesting was in the objects and the morphisms were boring. Here we start with boring objects and interesting morphisms. So our object here is just the point. So just a singleton object. And our morphisms are elements in A. So we only have automorphisms of point. Composition of our morphisms is given by multiplication in A. And our associativity, well, we should talk about tensor structure first before we talk about associativity. So our multiplication structure on objects is just that point tensor point is of course equal to point, and A tensor B on morphisms will be AB. So again, here our associativity is the identity, but we do require that A is an abelian group in order for the multiplication and the composition to be able to be interchanged with each other. This basically falls out from an Ekman-Hilton type argument. Okay, so those are two kind of boring examples of two groups, but we can actually think about combining these two in a kind of interesting way. So for the remainder of this talk, we're going to be talking about finite group Gs and abelian group As, and then we'll have these three cocycles, alpha. And so a three cocycle is a function from three copies of G to A, where for all G, H, K, L in G, we have this cocycle condition, which is that we have alpha of H, K, L. So we leave off the G to start. Then we bring in the G in the first term. You move over the H, move over the K. Whoops, alpha. And then push out the L. And this needs to be equal to 1. So this is what we'll keep referring to as the cocycle condition altogether. So these are just functions that have this condition for all G, H, K, and L in G. We call a three cocycle normalized. If alpha of G, H, E is equal to alpha of G, E, H. So E here is just the identity in G. And it turns out that every three cocycle is cohomologous to a normalized one. So primarily we will use normalized cocycles throughout this talk, and we'll justify why that's okay in a second. But the important thing is that any three cocycle would be cohomologous to a normalized one. Okay, so given that data that we just started with, we can define this two group curly G, where the objects are the elements of our group G. And the morphisms, so hom G of GH. So our morphisms will be equal to our abelian group A if G is equal to H, and we'll have no morphisms if G is not equal to H. So what this means in particular is that we have a skeletal two group, meaning that the isomorphism classes are just the singletons. So in particular, when we talk about weak inverses now, that means that when I look at X tensor Y, if Y is a weak inverse for X, it's not just isomorphic to one. As objects, they're actually equal to one. But there may still be an interesting morphism that's witnessing the fact that X tensor Y is isomorphic to one. Our multiplication comes from G. So G tensor H is equal to GH in G. So along the same lines as what we were just talking about with the weak inverses, as objects, we have that G tensor H tensor K is equal to G tensor H tensor K, right? These are just objects in G. It doesn't, G is a group, so it doesn't matter in which order I do my multiplication. However, because we're working in this two group setting, we can have a non-trivial associator here. So where associator may not be the identity. So we actually need associativity, morphisms from G tensor H to G tensor H tensor K. And we define these to be these alpha G H K, which is an element of A, which is equal to the set of morphisms from GHK to GHK. But in order to check that we actually end up with an associator, we need to check that this follows the pentagon axiom, right? So by the pentagon axiom, when we're dealing with a monoidal category, we could think about multiple ways of multiplying for or tensoring four objects together. So one where we have all the parentheses on the left and where we have all the parentheses on the right, and either path that we take to get there should be the same. So if we look at what we do with the associators here, this is alpha of, we keep G and H tensored together, but we move this set of parentheses over to here. And then here we keep the K and L together, but we move the GH parentheses around. Over here, we move inside these GH parentheses first. So this is alpha GHK. Then we fix the HK parentheses in the middle. And over here, we keep the G on the outside and switch what's happening in the HKL. So saying that this diagram commutes is actually identically equal to our co-cycle condition. So we can think about these three co-cycle conditions and this associator, this pentagon axiom associator condition as interchangeable. Okay, so this example of a two group is going to be our main kind of touchstone example. And so we say that a two group is finite if it has finite isomorphism classes of objects. So if we start with this finite group G, like we just talked about, it's not just that we have a finite number of isomorphism classes, we actually have a finite number of objects. So it's like especially finite. And then there's a theorem from, well, written up in Bayes and Lauda, but it's originally from Sin, who I just learned was a student of growth in DX in '75. He actually went to Vietnam and was giving a series of lectures, and she was his note taker for that. And they ended up starting a correspondence, and she got her PhD over correspondence when growth in DX went back to France, and she was in Vietnam. And her dissertation was handwritten, submitted from Vietnam to France, but it was never published. So Bayes and Lauda published it recently. I thought that was a cool bit of history. So the big theorem about finite two groups is that finite two groups are determined up to equivalence by this exact data that we just talked about. A finite group G, an abelian group A, and an element of the group cohomology. So it is possible that the abelian group A might have an interesting G action. In that case, it does change the definition of these curly Gs a little bit, mostly in how morphisms are composed, but we're not going to use any of those, so we won't go into detail on that. So because we're using this element of the group cohomology without loss of generality, we can just assume that we've chosen a normalized alpha, since, as we talked about before, every 3 cocycle is cohomologous to a normalized 3 cocycle. And in particular, this theorem means that all finite two groups have an equivalent skeletal two group, since the way that we've constructed these finite two groups from this data gives us skeletal two groups. So it's actually possible to see this curly G as a combination of G and point mod A. So we have a short exact sequence of two groups from 1 to point mod A to curly G to G to 1. So we can actually see G as an extension, or curly G as an extension of our finite group G by point mod A, a two group extension. So this short exact sequence splits exactly when our cocycle alpha is a boundary, and then isomorphisms between potential Gs that we could fit into this point, where we have identities coming down to another short exact sequence with the point mod A and G, correspond to 2 cochains. So you may recall that A extensions of G are classified by the cohomology group in the 2nd degree. So similarly, point mod A extensions of G are classified by these 3 cocycles. And this is G is fancy G is a central extension of G by point mod A, exactly when the action of G is trivial on A. So again, that case that we've looked at. So one interesting example of thinking about two groups in this way is the string group. I'm not going to go into a ton of detail about what the string group is, but just in case this is something that you've been thinking about, we have the spin group and the string group that come out of the, or one way that you can think about them is coming out of the Whitehead tower on the orthogonal group. So there's been descriptions of the string group before at a group level, but they're infinite dimensional and they're difficult to work with. So Schomer-Priest is really the one who went through defining all these ideas about a central extension of a two group. And he showed that you can think about the string group as a central extension of the spin group by point mod U1. So that means that we've now gone up a level categorically, right? We're no longer talking about groups, we're talking about two groups. However, we end up with a finite dimensional model. We do this with the 3 cocycle, that's the generator of the third cohomology of the spin group. But if we had chosen the generator 1 versus the generator -1, while we get abstractly equivalent two groups, they're not actually equivalent as central extensions, because when we would write the other short exact sequence here, whatever we would describe that one as fitting in, this map here would not be the identity. This would be an involution map instead. However, the thing that we would get here again would still be equivalent as two groups to the string group. So no matter which way we wanted to define the string group, we would end up with up to equivalent, something that's unique. And so thinking about the string group and spin group and SO, we can actually give a specific way to generate a two group from a representation of a finite group. So we start with our row naught, and then we can pull back to get G with fiber Z2. So this is giving G as a central extension of G0 by Z2. And then we have the string group living over the spin group. We can pull back again. And so this gives our curly G as a central extension of G by point mod U1, where G is the central extension classified by row star of this alpha string generator. Okay, so if you're not comfortable with the string group or spin group, that's fine. We're not going to mention it again, but it's an interesting example and kind of one of the reasons why some of these topics were pursued in the first place. So as I mentioned, technically most of our work is for smooth two groups. The examples that we've seen so far can be thought of as smooth, and a smooth two group is a group object in the bicategory of smooth stacks. So there's a few different equivalent descriptions of the bicategory of smooth stacks, but in particular, you can think about it as objects with Lie groupoids, one morphisms that are bibundles, and two morphisms, isomorphisms of bibundles. Again, we're not really going to deal with the fact that our groups are smooth and what we're talking about today. But when we do talk about these group objects in a bicategory, because we're working in a bicategory, note that the group axioms are not going to actually hold on the nose. They hold up to a specified two isomorphism, which will have to satisfy certain compatibility conditions. So we can see all of the examples that we've thought of or that we've looked at already as smooth two groups, which is really the important part that we want to take away. Okay, so we're going to talk now about principal two group bundles. And we're going to just kind of like talk about these abstractly, very briefly. And then, as I said, we'll talk about the specific case where we have these oriented two manifolds. So there are several ways that you might think about trying to define principal two group bundles. So what you probably want to do first is to think about what we mean by principal G bundles. But of course, there are many different ways to define principal G bundles. So you could think about them as maps into classifying spaces. You could think about them as some locally trivial things with transitive actions. You can think about them as flat bundles. You can use holonomy. So one thing that you might want to do is to take any one of those methods and try to bring it up a level in categories. And so it turns out that we can show that under the right conditions, all of the kind of constructions that you would do are equivalent. And then the other approach that you might want to take is say like, well, there are concepts of infinity groups and infinity bundles. And so maybe we just want to truncate at the two level. But our goal with this project was to really give some more explicit definitions of these objects, and very explicit in the case of the two manifolds. So starting with this really abstract thing didn't seem to be so useful. So we take Schomer-Pries's definition of principal two group bundles, which is that a principal G bundle on X is going to be a smooth stack P over X equipped with this G action, which is locally trivial. So in other words, we're going to have this surjective submersion from Y to X and an isomorphism of G stacks over Y. So we actually have that these both live over Y. And so if you are familiar with principal G bundles and thinking of them in the locally trivial definition, this definition should seem mostly familiar to you if we changed the fonts of our P's and our G's to just regular letters, and we remove this idea about stacks in here. This should seem familiar to the principal G bundles. However, it is slightly more complicated, right? Since we have this extra categorical structure, when we talk about these isomorphisms of G stacks, it's not quite the same thing as an isomorphism of G actions. We have things that are now only defined up to equivalence. And we also need to have a clear idea of what we mean by a G action here. And essentially, it's going to be these maps of stacks. P from G to P and two morphisms that give us the unit and the action. So because this principal two group bundle definition really comes from or has living inside it this principal G bundle definition, we actually get this functor from pi G to X to bund. Where here, this is the bi-category of principal G bundles on X, and this is the category of principal G being the two group version of G, and then this is the category of principal regular G bundles on X. Okay, so this is kind of the main definition that we use in our paper, but it's not the definition that we're going to work with so much today. But the other thing that we should touch on quickly are flat principal G bundles, which are principal G delta bundles, where G delta is given the discrete topology. But since we've been working with finite groups, we've endowed them with the discrete topology anyway. So everything that we've looked at so far has been flat bundles. When we work with these finite two groups, they're always flat bundles. And so one thing that you may be familiar with, again, from the regular one-dimensional setting, is that flat G bundles over X are classified by homomorphisms from pi 1x to G. And so in the case that we're dealing with an X with a contractible universal cover, we've proved that flat principal two group bundles are classified by homomorphisms of two groups from pi 1x to this two group G. So we'll talk in a second about what a homomorphism of the two group is, but here we're thinking about pi 1x in that very boring way of the first example that we saw of two groups. And when we specify to flat principal G bundles, we can also restrict our forgetful functor to just the flat principal bundles. So we're really going to work with this definition of flat principal G bundles for the next bulk of the talk. So we're going to think again about X as an oriented two manifold. In that case, we have the contractible universal cover, so the previous theorem applies. And we're going to think specifically about a torus as our example. So we want to understand the bicategory, which is the bicategory of functors between the bicategories point mod pi 1x and point mod curly G. So this notation is unfortunately a little bit confusing because this now means something, well, in the point mod pi 1x sense, it essentially means the same thing, but in the point mod G sense, it means something different. We're actually thinking now about how you can consider monoidal categories as bicategories with a single object, right? So we've taken these bicategories that we're talking about here, each have a singleton object point, and then the morphisms are the objects that were in the original two group, and the two morphisms are the morphisms from the original two group. And thinking about it that way makes it a little bit easier to describe the objects and morphisms that are at play. So if we think about what it would mean normally to have a functor from point mod pi 1x to point mod g, an original group G, essentially all this is a homomorphism from pi 1x to G, right? So on objects, these are just categories right now. On objects, we're just going to do point. We need to know what happens to our morphisms, and that's just looking at a homomorphism from pi 1x to G. So on objects, but when we think now about this two group case, it's not enough to just have this homomorphism rho. Our objects are now going to be pairs of a rho and a gamma. So the rho is as in the one-dimensional case. And then we need to, lift that rho to point mod G. So we also need this gamma from pi 1x cross pi 1x to A. So this is going to be providing us with isomorphisms in G, gamma of AB, which will be from rho of A, rho of B, to rho of AB. So again, rho of A, rho of B, and rho of AB are equal as, in this case, morphisms in point mod G, right? But because we have this higher categorical structure, we need to have this isomorphism that witnesses how they're equal to each other. We also need to have rho and alpha satisfy a compatibility condition, which is that D gamma has to be equal to 1 of rho star alpha, or in other words, that gamma of BC, oops, ABC has to be equal to 1 of rho of alpha of rho of A, rho of B, rho of C. And this compatibility condition comes from basically the idea of like weak monoidal functors, making sure that the associativity lines up, or we can think about this as also checking that when we talk about pseudofunctors of bicategories, we have to, when we talk about pseudofunctors of bicategories, composition and identities are only preserved weakly. So this is kind of the compatibility condition that falls out of that. Okay, so those are our objects in our in this bicategory that we're defining. So again, these objects are really just functors from point mod pi 1x to point mod G. And this is the same idea as looking at a homomorphism of two groups from pi 1x to our curly G. Now, when we talk about natural transformations from rho 1 to rho 2, back in this case, that consists of a T in G such that T of rho 1 of A is equal to rho 2 of A T for all A. in pi1x. And that condition may seem kind of like random at first, but if you just draw your natural transformation diagram, it's obvious that that's what it has to be, because their morphisms are only coming from the elements of G. But in this higher categorical sense, again, we need this extra piece. So our one morphisms are these T etas. So the T is as in the one-dimensional case, but our etas are these functions from pi1x to A. And these give isomorphisms eta A from T rho 1A to rho 2A T. So again, we have something that's witnessing the fact that these things are equal. Because and there's also a compatibility condition there, which is a little bit more complicated, so I won't go into writing that one down. So plus. And then on the one categorical column, we don't have any two morphisms, but in the higher dimensional, we do need two morphisms. And it turns out that our two morphisms, of course I run out of room, are just given by elements of A. And we only have a morphism from T eta to itself. So there are no two morphisms between non-equal one morphisms, and then the two morphisms are given by A. And the compatibility conditions that we would need to satisfy in general here turn out to be trivial. Mostly because there are no non-trivial two morphisms in point mod pi1x, since pi1x started with no non-trivial one morphisms. So it's complicated to explain all of those without writing out a ton of diagrams, but if you write out all the diagrams of what all these definitions are, there's kind of only obvious ways to define all of these as they come out. The compatibility conditions part is certainly a little bit harder to see where that comes from. But we can identify, it turns out, this earlier definition of flat principal two group bundles. We can show that this is equivalent to this bicategory. And also we know that our category of flat principal G bundles over X is equivalent to the category of point mod pi1x. So this comes from holonomy. And this is also equivalent to the morphisms from pi1x, just the regular group homomorphisms to G. So looking at the action groupoid, where we give the action of G is by conjugation. Right, so the action groupoid is a category where the objects are these, the objects in this set. So in other words, homomorphisms from pi1x to G. And then we have morphisms between those objects exactly when they're identified by the G action. So we've talked about that we have this forgetful functor pi. So we can construct the same functor over here, pi, or a similar functor. But the idea now is that we have this G action that's happening over here. And so we should be able to lift that G action to up here. So we actually show that that G action does lift. It's still a G action, to be clear, not a curly G action. And then that ends up giving pi the structure of a cloven 2 fibration. So if you think about fibrations in general, having a fibration means that if you have two objects in the downstairs and a morphism between them, and you have a lift of one of those objects upstairs, you can lift that morphism, right? So since morphisms down here exist exactly when the G action is giving that conjugation, so the morphisms are entirely defined by that G action, knowing how to lift the G action to the upstairs would tell us exactly how to lift those morphisms. So the main part of the paper that my work focused on was understanding what it means to have a G action upstairs. Okay, so what exactly does it mean to have a G action on this bicategory? And for the sake of not having to write it over and over again, we're going to just call it C. So what that means is that for all G in our G, we need a, technically you might call it a pseudofunctor, but when you talk about functors of bicategories, people usually assume that you mean a pseudofunctor. FG from C to C. And then, so this is telling us how each G is actually acting on C, this functor. And then we also need, for all G and H in G, a natural isomorphism. FG from FG composed with FH to F of HG. So this is telling us that these functors are actually assembling into a group action. And so when we talk about pseudofunctors, again, what we mean is our functors that are preserving identity and composition only up to a 2 isomorphism. So in order to define these functors FG on objects, we're going to call the image of them rho G gamma G. So we have to define what we think rho of G should be and what gamma G should be. And then we actually have to check that those definitions do in fact give us an object in C. In other words, we have to check that they do follow this compatibility condition. So because we want to lift this G action that we had downstairs on HOM pi1x G, that means that we should lift rho to just the conjugation of rho by G, since that's what's happening downstairs to morphisms from pi1x to G. They're being conjugated by elements of G. So we take rho G of A equal G inverse of rho of A G. And we choose a way to parenthesize this since we have these associators that, again, while things might be the same as objects, we need to keep track of what's happening or what's witnessing that they're the same object. And so then we need to define a gamma G of AB, which is going to take us from rho GA, rho GB, to rho GAB. So in order to do that, we draw one of these big charts, and these are the types of charts that we have all over the place when defining these FGs. So basically over here is the rho G. So this is rho GA, rho GB. What we wanted over here was rho GAB. And then we're just moving parentheses around using the associator until we can get this G and this G inverse right next to each other. And then we can get rid of those using the unit. And finally, we can reassociate so that we can apply the gamma that we had. Since we did start with an actual object, we had this gamma AB from rho A, rho B to rho AB. So our gamma GAB is actually defined to be the association of these, the composition of these things. So then, of course, we have to actually check that now this gives us an object in our bicategory. So just to give you an idea of what doing that involves, I'm not going to go over this in any sort of detail, but basically you're starting out with this thing of tons of applications of the cocycle, and then you're using the 3 cocycle condition over and over again. So this is, oops. So this is just, don't know why you're doing that. Okay, so this is an, I guess I can't write on it. An example in purple of using the 3 cocycle condition on 4 objects, and then you're kind of like looking back at the last piece and seeing where things cancel out and doing that over and over again until you can simplify down to 1. So we have lots of proofs like this throughout our paper, or rather we've done lots of proofs like this for our paper. As you can see, we haven't, or as you can anticipate, we haven't included all those details because I'm not sure how informative those details end up being. But I think it's interesting to kind of see the behind the scenes work of how these things come out. Okay, so there were a lot of technical details in just understanding what FG does on objects. So we're not going to talk about what it does on 1 morphisms or 2 morphisms because it gets more complicated, or even seeing this natural isomorphism, but that's the kind of data that we've assembled to give these this G action on that bicategory. So one cool application of this work is to the Fried-Quinn line bundle, if you're familiar with that. So we start with a G, a finite group, and we keep A as U1 and let alpha be a 3 cocycle. And then Fried and Quinn for oriented topological surface have constructed this line bundle, the Fried-Quinn line bundle over, oops, sorry, that's doubled up on X's, over flat G bundles on X. It depends on alpha, and the global sections of this line bundle are the value of Chern-Simons theory on X for the group G and alpha. And when you restrict this to the moduli space of principal G bundles over elliptic curves, so basically looking at all of these different collections of these flat G bundles on X for X's elliptic curves, we can obtain a line bundle, which Nora Ganter showed is the home of twisted G equivariant elliptic cohomology. So what we've shown is that this 2 fibration that we put together, I guess I really messed up with my X's, categorifies the Fried-Quinn line bundle. And so when we actually have that X is the torus, we can give a explicit definition of the transition functions of the line bundle in terms of elliptic characters. And these turn out to be precisely the elliptic characters that were introduced in a paper by Phillips as well. So it's one of these nice things where things that started out as seemingly disparate topics have kind of aligned. Okay. So thank you.
Okay, on behalf of everyone, I would like to thank Emma. Are there any questions? So I have a few questions. So my first one is, where does the motivation for the 3 cocycle condition come from?
I mean, it's so the 3 cocycles are kind of a common thing in group cohomology. There are like 2 cocycles and 1 cocycles as well. So they all kind of have this analogous structure of like a 1 cocycle would be something like eta A, eta AB, eta B being equal to 1. You have this idea of like moving elements through constantly. I haven't studied a ton of group cohomology other than just like using these cocycles, so I'm not sure where exactly they came from in the first place.
Yeah, thanks.
You had this example of the string group. Could I ask you about it?
Yeah.
As in the string group is naturally a true group. Can you keep going in this tower?
You mean like going with
3 groups?
Whitehead tower would be next? I mean, yeah. I think theoretically, but I haven't thought about that. Shomer Priest's paper gives like a really good introduction to the string group, and I would imagine that he might talk about it a little bit in there.
All right. I'll check it out. Thanks.
Even though you haven't thought about it, do you expect that working with 3 or 4 groups could be similarly concrete?
I'm not sure. I think it's possible if we keep kind of like restricting what we do with X, like how concrete things get. I think that's something that some of my collaborators have started to think about a little bit. But I don't know.
Okay, yeah. All right, well, if there are no other questions at this moment, let's thank our speaker again.